Hello everyone, my name is KOZACHKOV. I'm a graduate student at MIT in the Department of Brain and Cognitive Sciences, and today I'm going to talk to you about dynamic stability underlying cortical computations during working memory. So there's been an increase of interest over the last few years, both theoretically, empirically, and computationally, in how the cortex does what it does in a way that's robust to noise, perturbation, and just general distraction. And so we approach this question in a few ways, and so now I'm going to take you through the experimental paradigm we use to address this. So we had an animal, in this case a non-human primate, fixate on a screen. Then it was shown a sample image, in this case a banana, followed by a delay period, and halfway through the delay, randomly, on 50% of the trials, we showed a distractor image. The distractor went away, the delay was finished, and then the test period began, during which the animal had to saccade to the sample image that was shown in the beginning. In this case, it was a banana. To do this task correctly, the animal has to ignore the distractor. So we call it a distracted delayed match to sample task. While the animal was doing this task, we recorded from the PFC because that's the brain area thought to be most involved in working memory capacity. And we recorded from both hemispheres, dorsolateral and ventrolateral PFC. What we found is that the animal was able to do this task very well, above 95% accuracy, meaning that its neural computations were robust against the distractor. But we wanted to measure this robustness in a more quantitative way. So what we did is that we trial averaged trajectories, in this case on sample A, and also trial averaged them on the distracted trial, so sample A distracted. And then we measured the distance in state space between these two trajectories and followed that distance over time throughout the trial. So on this plot, on the y-axis, we're plotting that distance I was just telling you about. And on the x-axis, we have time from sample onset in units of seconds. So this black line here corresponds to the distance that we measured. And as expected during the sample period, shown here in green, the distance doesn't increase substantially from the baseline. However, upon presentation of a distractor, the distance increases, meaning that the distracted and the undistracted trajectories go separate ways. Importantly, we find that after the distractor is removed, the distances go back to their pre-sample baseline, indicating robustness. However, we also found that these trajectories do not carry strong sample information about the sample that was presented. So what do I mean by that? Well, we trained a decoder on the neural data. So this is a machine basically that you pass the neural trajectory to at each time, and you ask it to predict the sample that was present on that particular trial. And then we test the accuracy of the decoder on held out data and plot it over time. So what you're seeing here is the decoder accuracy on the y-axis and time on the x-axis. And so you should see that when the sample is presented, the decoding accuracy shoots up. But importantly, it drops down during the delay period and doesn't noticeably change during the distraction. So the question is, how is the animal doing this task at 95% accuracy and above when the information in the neural trajectories about the sample are very low? So there's not a lot of information during the delay. Well, we're not the first people to think about this. And basically, the community has posited a different view of working memory as opposed to just carried in spiking alone. And so it's called activity-silent working memory. And we're going to test two classes of trained recurrent neural networks trained on the task. One class has just spiking, and the other has spiking and short-term plasticity, and see how they compare to the actual neural data. So specifically what we did for the spiking only RNNs, we just trained a decoder on the neural trajectories because that's all we have access to, and again asked it to predict the label of the sample on that trial. But for the spiking plus STSP RNNs, we had access to the synaptic weights, so we trained two different decoders, one on the neural state space and the other on the synaptic state space, and asked them both to predict the sample identity. And so it's worth mentioning that we're not the first people to do this. This kind of modeling goes back to 2008 in a paper in Science by Mongillo and more recently by Moss et al. But the twist here is that we also trained a provably stable anti-Hebbian / inhibitory Hebbian model that we published last year because we hypothesized that the stability of this model would increase the robustness of the cortical computations it was modeling, and that turns out to be the case. I'll show you that in a bit. For now, let me show you what these decoder accuracy plots look like. So again, on the y-axis, we have decoding accuracy. On the x-axis is time. And what you're seeing here in black is the neural decoder. So for the RNN with spiking only. So when the sample comes on, you see the decoding accuracy shoot to a very high level, and it basically stays there throughout the whole trial. Now remember, this is completely unlike what we saw in the brain, where the decoding accuracy there went up for the neurons and dropped down during the delay. And so now let me show you for the spiking plus short-term plasticity model. Again, let's follow the black trace. That's the neural decoder. So it jumps up when the sample is presented, but then it goes back down to essentially baseline, which is what we see in the data. However, the synaptic decoder stays at a very high accuracy essentially throughout the whole trial. And this is what people talk about when they talk about activity-silent working memory. So people have posited that storing memories in this way through synaptic plasticity rather than persistent neural spiking is metabolically a better strategy for the brain. And that may be true, but we also find some evidence here to suggest that STSP models are more structurally robust than these fixed synapse models. So on the y-axis here, I'm showing you the accuracy of the network on the task, so 1 being it does the task perfectly. And on the x-axis, I'm showing you the amplitude of noise we injected into the RNNs while they were doing the task. And then each of these lines represents a type of RNN. So the PS class stands for plastic synapse, the FS stands for fixed synapse. And so what you should see is that all these networks degrade essentially in the same way, no spectacular difference. But when we tried a different type of perturbation, namely we randomly ablated a certain fraction of synapses in increasing quantity, we found something more dramatic, which is that the plastic synapse networks lasted much longer with respect to this perturbation, whereas the fixed synapse networks degraded very quickly, suggesting that perhaps a reason for using short-term synaptic plasticity in this way is to be structurally robust. And I'll just point out that this PS head model is the model I was talking about from our paper last year, which is provably stable. And that turns out to have consequences for both this injected noise over here and the structural robustness. So it's the most robust out of the models we tested. So to conclude, we found that neural dynamics in PFC are robust against Distractor, but they do not carry strong sample information across the delay. Trained RNNs with STSP explain the neural data better than fixed synapse RNNs, and STSP RNNs are more structurally robust than their fixed synapse counterparts, suggesting a possible role for STSP beyond metabolic efficiency. I'd like to thank my collaborators and advisors, in particular Earl Miller, Jean-Jacques SLOTINE, and John Tauber, Michael Lundquist, and Scott Brinkat. Thank you all for listening.